Welcome back. In this lecture, we're going to be discussing about genetic algorithms. What are the basic terminology? What are the basis of these kind of algorithms? Well, first of all, we go in detail about understanding genetic algorithms. Let's see what are the typical applications. Why do we need a genetic algorithms approach? In principle, as the name suggests, genetic. It came from the medical science, biological terms. It has this approach has applications in many areas of engineering. As you know, many of real-world problems are NP-hard problems, and we solve those kind of problems via different approaches. Mostly of those approaches are approximation kind of algorithms. Okay. The genetic algorithms, they have uses in computational protein engineering problems, gene profiling, molecular design, e-commerce or online marketing, optimization, adaptive computation, automotive design, encryption and code breaking. In financial markets, when you have to predict buy and low signals, let's say in foreign exchange market, your algorithm is trying to understand or trying to intelligently model so that it can give you a buy signal and a sell signal, which you can make use of for trading in financial markets. Evolutionary computation. So such kind of algorithms, they are under the category of evolutionary algorithms. Okay, bioinformatics, robotics, computer gaming, electronic design automation. As you see, there are many areas of application of these algorithms. So let's try to understand what are the basic principles or basic terminology or basic idea about genetic algorithms. So first, let's try to understand from where the term came. As we know, all living beings, they have a cell. And inside the cell, there are many other things, but to make the life simpler, let's just focus on two chromosomes. A cell may have many chromosomes, and those, if we look inside these chromosomes, we can find that these have many strings of DNA. Okay? We don't want to get into details of these biological terms. There are many more terms, but for our algorithm purpose, we just simply focus on few terms. Chromosomes, in other words, these are candidate solutions to our problem. And we can represent these by the strings of 0 and 1. Allele. Allele is a term. It is nothing but either 0 or 1 in a bit string. Okay? In terminology, we call it an allele. Crossover. Crossover is nothing but an exchange of genetic material between two chromosomes. Okay? Mutation. Mutation is nothing but simply flipping a bit in a randomly chosen chromosome and at a randomly chosen locus. Okay. Now I said randomly chosen chromosome, but you can say, okay, I keep on looping on each chromosomes, then you don't randomly choose. But when your population is more, you can choose that way. There is no as such fixed terminology there. So mutation idea is that when, let's say, you are forming a new population, okay, a new population is identical, and you decide to change a bit or an allele at a randomly chosen locus or a point. So instead of 1, you decide to flip it over to 0, so that your new population have something different to carry on with the next level of generation. All right. So let's try to understand how crossover works. Let's say we have a string or a chromosome of a parent M and another string of 1 and 0, or a chromosome from parent F, and we want to do crossover. A crossover, you may think of, in other words, how to generate new population. Okay, so as in real world, male species and female species, new population is being generated via their union. Okay, the same way, the same idea of crossover at a randomly chosen locus or a point or crossover point. So idea here is that you swap the bits, swap these bits from a randomly chosen locus point from one parent to the other parent. So let's swap it. Okay, so we swapped these bits from parent F and given it to parent M. Okay, so parent M gives these bits to parent F, and a child 2 is born. In the same way, parent F gives these bits to parent M, and child 1 is born. The idea of crossover is simply swapping the bits from one parent to other parent. All right. Mutation, as we said earlier, that it's a flipping of a bit at a randomly chosen locus. So let's say before mutation we have this chromosome, okay, and after mutation we have this chromosome. Notice here we flipped the bit at this locus point from 0 to 1, okay, or we flip this allele to 1. All right. Another important concept is fitness function. So what does it mean by the fitness function? Well, it simply tells us that whatever is the new population I have generated, okay, how good is that population? So that fitness function basically evaluates the goodness of a potential solution. Or in other words, two parents, okay, through their union or through crossover, in our terminology, we say new children are born. Now, out of those children, some children may not be that good as per our criteria specified via fitness function. So we can discard those children in our population and try to generate new children, and then evaluate the goodness of those children via our fitness function. Okay, so that only the good solution they will remain and will continue to the next stage of evolution. All right. Typical example, for example, a fitness function fx is x plus sine x. Now x, you may think of a string of 0 and 1, okay, or chromosome, and then when the new set of children are being born, so you can pass through those set of strings And if those set of strings or new children pass through this fitness function, then only you allow them to be a part of population to take that population to the next stage of evolution. All right. Now let's talk about the method. It's a very simple method, generic genetic algorithm method. So step first is very simple, that you start with a randomly generated population of n m-bit chromosomes. What it means that you have some number of chromosomes, and each chromosome have a certain length or certain number of bits. Okay. In this step 2, you calculate the fitness of each chromosome in the population. And if the fitness function is a filtering criteria, so you filter all those chromosomes. Only the good chromosomes, they will filter through. The bad chromosomes, you discard them. In step number 3, okay. So step number 3 says that you repeat following steps until n offspring have been created. What is the first step? A, select a pair of parent chromosomes. Okay. And how do you select? Well, you select using some probabilistic technique, or with some probability of selection. Okay. And that probability of selection should be such that it's an increasing function of fitness. So you have selected 2 parents. Okay. And then next step is simply that with certain probability, or you may call it crossover probability, you do crossover between parents. What it means that not all parents will do crossover. You may think of in a simple way that not every couple will produce babies. All right. So with a certain number of probability, crossover probability, okay, you cross over 2 parents, and the kids or children are born. Okay. And now we already said that how to do crossover. So how to select the locus point? Okay. So that again we randomly choose that point or crossover point with a uniform probability to form 2 offspring. All right. Now the third step is mutate. Okay. Not every time you want to mutate the 2 offspring. So there is a certain probability of mutation. You may call it a mutation probability or mutation rate. With that probability or rate, you mutate and place the resultant chromosomes in the new population. All right. So we do 3 steps, A, B, and C, okay, until we have n offspring, or our original population n. You see, we selected n chromosomes in the beginning. Okay. So the idea of this step 3 is that we produce n offspring, so that we replace the entire population which we had originally. And when we have the new population, then we just replace the current population with the new population. Or you may think of, in other words, that old people, they are dead, okay, and new generation or new people or have taken place. Let's say your grandfather, he is no more there, so his place is taken by your father. Very simply way, the retirement of the population. So you no more need the old population, you need the new population which you have generated via crossover and mutation. Okay, and now number 5th step, you go back to step number 2, and you keep doing that procedure for how many times? Well, it depends on how good the solution you need, or how far you are from your goal. Okay, or in other words, goal oriented programming. So typically, 500 to 1000 times you repeat these steps. Depends. So there is no fixed criteria. All right. So these are the basic steps for genetic algorithms. Now, as you can see here, that at each step we are making use of probability, or in other words, statistical technique. So it becomes very important that we have some idea of probability and statistical estimation techniques. And depending upon those probabilistic estimations, the quality of the solution may change. All right. So I hope you guys have enjoyed this lecture. We're going to be doing more lectures for different class of problems solving via genetic algorithms. Thank you very much for liking and subscribing LEPROF on YouTube. If you have questions, if you need more lectures, if you have you are struggling with any subject, you may contact us for private consultation. And we appreciate your feedback and support. Those who have not subscribed, please do subscribe. Have a wonderful day.